Welcome to Maths with Bob. Today we're looking at conics and in particular the ellipse. And what do we know about ellipses? Well, basically they're ovals, I guess. You can see here I've mentioned a few things. You can think of them like some sort of squashed circles or circles with a different aspect ratio. I guess you could think of them like this. But normally we look at the equation centered on the origin, which is this one, x squared on a squared plus y squared on b squared equals 1. We can obviously change the origin to hk, and then that would be x minus h all squared on a squared plus y minus k all squared on b squared equals 1. That would be the ellipse with center hk. We are normally also assuming that a is actually bigger than b. There's you can see here a couple of ways to represent the ellipse. There's a Cartesian and a let's have a look. Let's see if we can get the Cartesian one. Okay, which is this one here. Okay, this is the Cartesian one, and we can actually just go down and have a quick look at the parametric one down here. So that would be the parametric representation of the ellipse. X is equal to a cos theta and y is equal to b sine theta. Now, a few things about this. If we're actually ellipses are usually, I'll just see if I can spin this around for us. Let's see if we can spin it around. Okay, here we go. You can see here, depending on whether A is bigger than B or B is bigger than A, we get a different sort of shape on our ellipse. Okay, we can sort of, but normally now we have A is bigger than B, and the ellipse is looking like a football, I guess you could say. Okay. Now, the eccentricity of an ellipse is in fact always between 0 and 1. A circle has actually eccentricity of 0, and a parabola has eccentricity of 1. And if you may have watched the other video on these conic sections, I'm going to show you a few other things in a little while as well. But this is actually how we derive, if you like, the equations of the focuses and the directrices. We just use what's called internal and external division, okay, and we set up some equations and we can actually show where the focus and directrices are. Now, you can see here eccentricity is in fact a ratio. It's, if you can think of it like a measure of the deviation from circular, I guess. Okay, the bigger the number for the eccentricity, the more I guess the deviation from the circle, or if you like, the stranger the circle is, or the flatter, or if you like, the more football shaped the circle becomes. And as you go past 1, you get into the hyperbolas and it goes completely crazy. Okay, let's actually have a look at some of these. Okay, we're now looking at a GeoGebra file. You can see I've actually set up, well, I can actually change the eccentricity. You can see here I'm just changing the eccentricity. You can see that its dotted lines are in fact the directrices. Okay, we can actually take the point and have a quick look here. Now, I've got actually the lengths of P to S and F, the foci, are in fact G and H. And if you can see here, on the G minus H is in fact changing quite dramatically. Over here, if you have a look at the over here, you can see here G minus H would in fact change quite dramatically if I start moving this. Okay, but G plus H is in fact stable at 4.6 at the moment. Okay, this is obviously one of the properties of ellipses. Sum of the focal lengths is constant to that particular point. Okay, all right. So let's actually start changing. I can change the A now. If I can, you can see here what's happening now. If I actually change the A, let's actually change the eccentricity as well. Let's actually turn it well more circular. So if what happens when a circle? Okay, we can see here the directrices are heading off to infinity, and at E is equal to 0, it's perfectly circular. Okay, and as I bring, you can see here now the okay, it's changing the eccentricity to about 0.7. You can see here now that the directrices are in fact approaching the foci, and I can see here if you can change the now. Okay, as you can just see, I'm just shrinking and changing it. But let's actually change the eccentricity to greater than 1. Okay, here we are. And pull the point up and have a look, and just have a quick look. I'll just move the point And you can see here, okay, the G plus H, okay, is changing, okay, but, okay, G minus H, okay, is in fact, okay, the same. So the difference in the focal lengths is a constant here for the hyperbolas. We're going to be looking at these next, the hyperbolas, but at the moment we're actually concentrating on the ellipses, okay. And let's drop the ellipse eccentricity back. Oops, going the wrong way. Down to here we are. There we are. Okay, here we go. Okay. Okay, well, let's actually have a look at how we find the eccentricity. Okay. Well, how do I find E, the eccentricity? Well, I need a definition. I guess you could say I need. We need this thing here. Oops. No, we don't want that. We don't want to move it. I just want to actually have a look. Ooh. Yes, there we are. It's a bit strange. But we need this particular ratio, PS equals EPM. We square both sides. We set up the distance formula, as you can see here, squaring both sides. I'll see if I can make that a bit bigger. It's a bit tricky to make it a bit bigger. Let's see if I can make it a bit bigger. Okay. Doesn't want to. Okay. All right. But we square both sides, basically. And I'll just get rid of that. Okay, so we square both sides, and we basically then divide by, if you like, here, a squared bracket 1 minus e squared. That's actually equal to b squared to set up the equation for the ellipse, and then we have an expression for E. So we can actually find E, the eccentricity, fairly easily with, well, we know the A's and the B's. And you can see here, we'll do a quick example in a second. E is equal to the square root of 1 minus b squared on a squared. Now, this has to always, as you know, lie in the range between 0 and 1. Okay. All right. So here we have a few examples. X squared on 81 plus y squared on 49 equals 1, or if you like, x squared on 9 squared plus y squared on 7 squared equals 1. Then I switch them around a bit. X squared on 7 squared plus y squared on 9 squared is 1. And you can see here the eccentricity is obviously the same. It's just that the orientation has been changed. Okay, you can see the foci are now plus or minus 4 root 2, 0, whereas in the other one it's 0 plus or minus 4 root 2. Obviously they are on the y-axis, and the first ones are on the x-axis. And you can see the directrices are x is equal to something, in this case plus or minus 81 root 2 on 8. And then for the example 2, they obviously switch to y is equal to plus or minus 81 root 2 on 8. Okay. Alright. Now, how do we find equations of tangents and normals? Well, this is fairly involved. We need to basically differentiate the ellipse, implicit differentiation, I think is the easiest way to go. Get an expression for dy dx, and then put in, if you like, x1, y1, or if you want the parametric one, a cos theta and b sin theta. Okay, well, let's have a closer look at this. Okay, here we are. Okay, this is the Cartesian gradient, which is, if you like, just putting in x1 and y1 for the x and y. So it's minus x1 b squared on y1 a squared. And if you just have a quick look below, obviously the normal is the negative reciprocal. If you go across to the parameter or parametric gradient, you can see here it is actually just substituting for x and y, a cos theta and b sin theta, and you can see here that the gradient for the parametric form is minus b cos theta on a sin theta, and obviously if you look down here you can see, okay, the normal's gradient is again the negative reciprocal. Not too bad. Now we have to start using these to get equations of tangents and normals and all sorts of things. So let's have a quick look. Okay, we want Cartesian equations. You can see here we need to put the gradient in, multiply both sides by y1 a squared, divide by a squared b squared, and eventually we'll get this quite important, I'll just see if I can, here we are, these are quite important, these formulas here. I've got them in boxes now. Okay, so this is the tangent, okay, which is x1 on a squared plus y1 on b squared equals 1. That's the Cartesian tangent to the ellipse, and obviously the normal. Okay, you have to go through a bit of working, but you can see here it says x a squared or a squared x on x1 minus b squared y on y1 equals a squared minus b squared. Okay, so that is okay, the equation, or if you like, the Cartesian equation of the normal to the ellipse at that particular point p x1 y1. Okay, now the parametric ones, okay, you still do a similar sort of thing. You have to put in the parametric gradient and the parametric point to try and simplify. You can see you divide by a and b, use the fact that sine squared plus cos squared is 1, and eventually you'll get over here. Okay, you get the what's called the parametric tangents equation, x cos theta on a plus y sine theta on b equals 1. And okay, doing a bit more work, you'll get the parametric normal. Okay, x or ax on cos theta plus, or sorry, it's actually minus by on sine theta equals a squared minus b squared. Okay, that's the parametric normal to the ellipse now. Okay, and obviously it's at that point a cos theta b sine theta from the parametric point. Okay, these are the parametric equations. Okay, now the chord of contact. Okay, the chord of contact is as you can imagine, it's pretty tricky to derive algebraically, but most textbooks use this technique that we basically, if you like, get the equation of the tangent and put the tangent at a and b and put x naught, y naught, which is the external point where you're firing the tangents from. So p is the external point, x0, y0, and you basically put the point in and then look at what sort of equation would they both lie on, and that's called the equation of the chord of contact. We do this for lots of the conics, this one down here. So, okay, so this is the equation of the chord of contact. It looks a bit like the equation of the tangent, actually. X naught x on a squared plus y naught y on b squared equals 1. Okay, so this is what's called the equation of the chord of contact. Okay, we're now going to have a quick look. I'll set up a GeoGebra file just to have a look at this. Well, okay, here we have a GeoGebra file, and I'll just have a quick look here. This is, you can see here, I'm moving my point P around. This is the, and you can see the chord of contact is in red there. Okay, this is the chord of contact. Oops. Okay, we need to be external to the. You can see as I approach, it looks like a bit like a tangent, doesn't it? Really. Okay, so here we have the equation. Okay, the chord of contact's equation, which is up here. Okay, which is changing as I move the point, obviously. Now, if I actually, I've got A and B here. You can see here we can change this. I've actually got the foci as well. You can see the foci now on the x-axis, and if I make B bigger than A, it goes onto the y-axis, and we still, obviously, the equations of chord of contact. We can move this anywhere we like, really. I'll move the point right across through the ellipse there, but obviously you can see here it's basically just a line which is basically formed by points of contact of the tangents coming from an external point P. Now I just wanted to show you one of the properties. There's lots of properties of ellipses. Let's actually see if I want actually a focal chord. Now a focal chord, as you can see, is actually going through the focus. So let's have a look. Okay, oh, there we go, a focal chord. Now the directrix will be out here roughly, it looks like about 13. So if I actually move that point P up and down along that line, you can actually see that that chord of contact is actually a focal chord. Now this is one of the properties of ellipses, that if I actually am on the directrix, okay, and fire the tangents off, the point of contact obviously forms a chord of contact, but it's actually a special one. It's called a focal chord. So the chord of contact becomes what's called a focal chord when I'm actually firing these tangents from the directrix to the ellipse. Okay. All right. Okay, well let's move on, and here we have the parametric chord PQ, which is a fair bit of trouble to actually derive. You need a fair bit of trig, because you've got to use sums to products and products to sums. This is fairly involved. I just did it quickly here to show you what's called the equation of well, this is actually the parametric chord PQ, coming from the points P and Q. You can see here with the parameters theta and phi. They're obviously on the ellipse. Okay, but this is actually quite a difficult equation to derive, and you would need to revise your sum to differences and differences to sums trig results. Okay. Now, this is some of the geometric properties. Okay. You can see here some of the focal lengths is constant. Yeah, the tangent equally inclined, the normals bisect angles. We just did number 3. Actually, I showed you number 3 on the GeoGebra one about the quarter contact from a point on the directrix is actually a focal chord. And for the tangents, okay, the part of the tangent between the point of contact and the directrix subtend a right angle at the corresponding focus. This is another property of the, or a geometric property of the ellipses. I'm not going to prove these, and you can see many textbooks actually go through the proofs of these. But just before we go, I just want to show you how you can actually draw an ellipse. Okay, well, just to finish up, I just wanted to show you this is basically the auxiliary circles method of drawing an ellipse. I have a point here. If you have a quick look, I'm just moving D on the outer or the major auxiliary circle. Now, there are a few things about the semi-major and semi-minor axis. The major axis obviously is the longest one. The minor axis is the smallest one, and the semi-major obviously is half the long one, half of A. Well, what is it? A would be actually the length of the major axis. Okay, in this case we have A bigger than B. Okay, and the whole length obviously is what? 2A. Okay. Yes, and a quick way to draw these obviously is if you let x equals 0, you'll get where it cuts a y-axis, which would be plus or minus b, and if you let y equals 0, you get plus or minus a. So you can see that in fact these major axis is in fact 2a, and the minor axis is length 2b. Okay, well, thank you for watching, and bye for now.